Okay, students, let's get started and do some more problems. So we're going to be looking at chapter 17, and we're on page, no, wrong spot, page 615. So let's look at number one. Very simple question. How long does it take light to travel through a 3 millimeter thick piece of window glass? So you got a piece of window glass here, and the thickness, okay, or we'll just say the thickness is 3 millimeters thick, so that's 3 times 10 to the negative 3 meters, or just 3 millimeters. Okay, use our prefixes. And we want to know the light ray coming in. How long does it take to pass through there before it comes out the other side? Okay. All right. Well, that's a real simple equation. We look at equation 17.1. And basically, we can use our velocity equation from kinematics, where delta x is equal to delta t. Of course, that's the average velocity. And so then we solve it for t, and that's going to be delta x over what? Delta what? Delta t, is that? No, excuse me. I'm sorry. That's going to be delta x over the average velocity, right? Average velocity. All right. Well, there's a problem, though. We don't know what the velocity of the light wave is. But we can find the velocity of the light wave by taking the speed of light and dividing it by the index of refraction. Okay? Now, it tells us that it is what? A piece of glass. So we're going to just assume that's flint glass. And so then the index of refraction is 1.5. So N for glass is 1.5. There's no units, okay? And you can find that in your text. I can't remember what page number that on, or the table is, but it's in your text. And so now let's just plug everything in, okay? So we're going to take the change in time, and it's equal to 3 millimeters, 10 to the negative third, and then take the speed of light, which is 3 times 10 to the 8th meters per second, divided by 1.5. And of course, that's a complex fraction, and so that's basically the same as saying 3 over 1 divided by 3 over 1.5. And when you do all that wild asinine arithmetic, you come up with what? Well, let's see. We say 3 to the negative third divided by 3 to the 8th divided by 1.5. And we get 1.5 to the negative 11th seconds times 10 to the negative 11th seconds. Okay? Or we could say what? 150 nanoseconds? Yeah. We could say 150 nanoseconds. All right. We wanted to use our prefixes. Okay. All right. That's number one. All right. Let's look at another one. Let's look at I think number 9 is the next one on my list. Number 9. Yeah. All right, so number 9, and that is same page, 615. Says 2 narrow slits are illuminated by light of wavelength lambda. So you got 2 narrow slits. 2 narrow slits are illuminated by a wavelength of light lambda. Okay, so we have a wavelength of light lambda. And the slits are separated the slits are spaced 20 wavelengths apart. Okay, what is the angle in radians between the central maximum and the M1 bright fringe? Okay, so we want to know what theta is. Okay, so it's lambda. The slits are spaced 20 wavelengths apart. So the okay, so they are 20 wavelengths apart. The slits are, and it says what is the angle in radians? So we want to know what theta is in radians. Okay, all right, not degrees but radians, between the central maximum and the M1 bright fringe. So if you were looking at, all right, you've got your slits here, your lights coming through, you got your screen right here. So you're going to have a central maximum, something like that, and then you're going to have another one here, okay, and something like that, okay, and that's not perfect, okay. So we want to know what? We want to know what is the angle in radians between the central maximum and the M1 bright fringe. So we want to know what the angle is from the central maximum to here. So we want to know what this angle is. We want to know what theta is in radians, right? Okay. All right. Well, we know, if we go back and look, go back and look in our text, okay, basically what are we given? We're given M1, we're given the D is 20 lambdas, okay, the distance, okay, is 20 lambdas. So now we've got to do what? We've got to find theta. So theta is defined as, theta is equal to the maximum, whichever maxima it is, times the wavelength divided by D, okay? Well, the central maximum, it was 1. Remember what it told us, from the central maximum to 1 maxa. So that would be 1, right? And we don't know what the wavelength is, but we're just going to assume that it's 1 since the distance is 20 lambdas, right? So we're going to say 1 over 20, all right? And that's going to give us what? Well, we've got 1 times 1 over 20, which is equal to what? That gives us an of angle in radians of 0.05. It's what we should get, right? 1 divided by 20. Yeah, 0.05 radians. And in order to convert that to degrees, we're going to do what? We would multiply that by what? So 0.05 times pi, I believe I'm doing this right. Let's see, or am I doing it backwards? Yeah, so we say 0.05 times 180 divided by pi, and that gives us about 3 degrees, okay? So it's going to be approximately 3 degrees, or 0.05 radians, all right? All right, so that's number 9. Now let's move on to another one. I think our next one I'm going to look at is number 24. Yeah, number 24. And that's on page 616, okay? All right, so let's look at number 24. Okay, so number 24 says what? Says there, what is the thinnest film of magnesium fluoride? So we just have a film, and I'm just going to do it like this, and I'm exaggerating it a little bit, okay? And so this is magnesium fluoride, all right? And the index of refraction of magnesium fluoride is N is equal to 1.38, okay? on glass. So that film is on a piece of glass. Okay, and there's our piece of glass. All right. That produces a strong reflection for orange light with a wavelength of 600 nanometers. So you got a thin film of magnesium fluoride right there, and this is the glass. Okay. And so when it reflects, we get a wavelength of orange that is 600 nanometers, which is 10 to the negative 9th meters. Okay. All right. So what is we want to know what is the thinnest film, right? We want to know what is the thinnest film that we can calculate, okay? Well, in other words, what would it be? What would be the thinnest film we could use, okay? All right, so we know we have glass, we have air. That's the index of refraction for the magnesium fluoride. What's the index of refraction for air? Well, that's 1, isn't it? 1.0. We'll just say it's actually on out a few more decimal places, but for all intents and purposes, we're just going to round it to 1, okay? All right. So now let's look at our equations. We look at a couple of different equations. I say a couple of them. We look at equation 17.14, and oh yeah, and don't forget too, the N for the glass, we just did that, is 1.5, isn't it? Okay. All right. So we know according to equation 17.14, we know that the lambda, the wavelength, is equal to 2nt over m, all right? And then if we solve it for t, which is the wavelength, okay? And let me read it again. It's saying what is the thinnest film? Excuse me, that's the thinnest film, not the wavelength. So the thickness of the film, all right? So we solve it for that, and so it is lambda c times m over 2n, all right? So we have and we choose 1 for the maxima, okay? All right, maxima 1. All right, so the wavelength was 600 nanometers. M is 1, okay? Divided by 2 times, and what was the thinnest film we want to know? Well, we know the index of refraction is 1.38 because it's we want to know what the thinnest film of magnesium fluoride is to get this reflection of orange light, okay, with that particular wavelength. And so we should wind up with, we got 6 to the 9th, negative 9th, excuse me. So we got 600, to the negative 9th. The negative 9th divided by 2 times 1.38, correct? And so we get about 217 nanometers. We get an answer of 2.17 times 10 to the negative 7th meters, but let's put that in nanometers. Let's just say 217 nanometers, okay? So there's your answer. There's your thinnest film that you can have of magnesium fluoride to get a strong orange reflection, okay? All right. Well, let's do one more. Let's look at number 37. Ah, no, 37. 37, all right. And it's on page 617. All right. All right, the second minimum in the diffraction pattern of a 0.1 millimeter wide slit occurs at 0.7 degrees. What is the wavelength of light? Okay. So we have the second minimum. All right. So that's maximum or minimum, excuse me, not maximum, but minimum. Minima. There we go. Got to get it out right. That's 2. And the slit distance is what? It's the diffraction pattern of 0.1 millimeter wide slit, so that's A, 0.10 millimeter. My pen just does not want to cooperate with me. Let's try this one more time. I'm sorry, y'all. All right, so 0.10 millimeter. That's A, that's the width of the slit. What is the wavelength of light? So we want to know lambda, don't we? So we have our minima, which is 2. We have our slit width, which is A. We also have the angle is what? Well, it's 0.7 degrees, but we need to put that in radians, don't we? Yeah, we sure do. We need to put that into radians. So let's put it into radians. So let's take our degrees. And so we say times pi divided by 180. Okay. And what do we get? Well, let's see what we get. So we get 0.7. And by the way, you don't have to put your calculator in radian mode because we're not doing trig functions with this, okay? You can leave it just like it is. 0.7 times, and you do need to use pi, the pi key on your calculator, however. Make sure you do that. Divided by 180. And we get 0.0122. So we get 0.0122 radians. So that's what it is in radians, okay? Now we can work the problem. Okay, so we know then that the angle the angle in radians is equal to P times lambda, and P is the minima. That's how we measure minima, okay? All right, over A. And so we want to find what? We want to find theta, don't we? Okay, or no, wait a minute. We want to find, what is the wavelength? We want to find the wavelength. So then we rewrite the equation. The wavelength then is equal to what? Well, we just solve for the wavelength, don't we? You always need to do this too. So it's A times theta P over what? Over P, isn't it? So let's plug everything in. So we've got 0.10 millimeters times 0.0122 radians divided by, and it was the second minima, wasn't it? That's P. P is minima. I should have said P, not M. Sorry about that. I'm thinking of maxima. No, we got to do minima, which is P. P, there we go. All right, that's a lowercase p. So put a 2 there. And so what do we get? Well, okay, we get 0.1 to the negative third times 0.0122 divided by 2. And we should get 6.1 to the negative 7th. So we get 6.1 times 10 to the negative 7th meters. But let's put it in nanometers. It'd be 617 nanometers. Maybe decimal 2 places to the right. Okay? Okay. Well, yeah, 617 nanometers. Okay? All right. Okay. And that's it for this chapter. I hope this helps.